proven the Collatz conjecture, the fundamental equation that defines the Collatz conjecture. We begin with a quote from Paul Erdos. Mathematics may not be ready for such problems. The proof by James P. Moore. The Collatz conjecture is an extraordinarily difficult problem, completely out of reach of present-day mathematics, according to Geoffrey Lageray. Lothar Collatz was a German mathematician born in Arnsberg, Westphalia. The 3x plus 1 problem is also known as the Collatz conjecture, named after him, and has been unsolved until now. Derek Mueller had this quote: "The Collatz conjecture is the most dangerous problem in mathematics, one that young mathematicians are warned not to waste their time on." The Collatz conjecture is based on a simple premise. Pick an integer x between 1 and infinity, and do one of these two things depending on whether it is odd or an even number. If it's even, divide the number by 2. If it's odd, multiply the number by 3 and then add 1. For example, if we chose x equals 7, 7 is odd, so we multiply by 3 and then add 1. That's 22. 22 is even, so we divide that by 2 to get to 11. 11 is odd, multiply that by 3 plus 1 equals 34, and on we go. Eventually, we end up with 4, then 2, then 1. Now, the conjecture is that any positive integer chosen to begin with eventually ends up with 4, 2, 1 every time. And it has for every number ever tested. But they don't know the reason why. It hasn't been proven mathematically until now. From part 1, we created what we call the subtraction machine. If x is odd, as you know, we multiply by 3, then we add 1. This increases x by 2x plus 1. That's called the amount added. This step always creates an even number. For any even number x, divide the even number by 2. This is the equivalent of subtracting 1/2 of it. Subtract 1/2 of the even number. The result will always be the same. Starting value x plus amount added minus amount subtracted equals result, odd or even, for each integer. Now, for all subsequent odd and even numbers, the process is repeated. Once the value of 1 is achieved, we find that the total amount added and subtracted during the calculations when applied to the starting integer value x will always result in a final value of 1. So we start with the integer value x. And then throughout the sequence of the Collatz, we add the total numbers added, we subtract the total subtracted, and it equals 1 every time. The machine itself has been proven to be infallible, but that's not good enough for mathematicians. The subtraction machine is not enough. To determine the equation of Collatz sequences, we need to add some notation. For dividing by 2, multiplying by 3, and then adding 1, we'll add a subscript to each process. For the first division of 2, it will read 2, little subscript 1, the first 2 that we use. For the second 2 we use, it will read 2, subscript 2. If required, the 10th division will be 2, subscript 10. Similarly, 3s and 1s as we move through the process. Let's begin with some very simple examples, starting with the number 2. 2 is even, so we divide it by 2, and it's the first one. 2 divided by 2 subscript 1 equals 1, and when we have reached 1, we have reached our goal, and the search is over. For the number 3, 3 is odd, so we multiply by 3, and since it's the first one, we have subscript of 1, and then we add 1. 3 times 3 plus 1 equals 10. We put that in a bracket. Within the brackets there, that equals 10. Moving on, because 10 is even, we divide by 2, or in this case, multiply by 1/2. Since it's the first 2 we're using, it has a subscript 1. When multiplied through, it equals 5. And in brackets now, we have the number 5 based on the processes that we've already done so far. Now 5 is odd, and is within those brackets is 5. We multiply it by 3. It's the second 3 that we're using, so we have 3 subscript 2 times 5 in the brackets plus 1, the second 1 that we're using, equals 16. 3 times 5 plus 1 is 16. So within the new brackets is 16 based on the processes so far. Now 16 is even. Everything within the square brackets is 16. Because it's even, we divide it by 2. It's the second 2. So we have a subscript of 2, and that equals 8. So in the new square brackets, that is equal to 8. And we move on to the next slide. Now 8 is even. We divide that by 2. Now we're into the third 2 that we've used. And in the same fashion, we multiply it through in the base, and we get that new square bracket, which is equal to 4, based on all the processes so far. Now 4 is even. We divide that by 2. It's the fourth 2 that we've used. We multiply that through on the base, and we end up 4 divided by 2 equals 2. So everything in that bracket is now equal to 2. Now 2 is even. We divide that by 2. This is the fifth 2 we'll use. We multiply all the way through on the base, and we end up with that bracketed expression based on 3 with 3 fractions that we have to deal with. When we simplify the fractions, we get 3 squared times the original 3 plus 3 divided by 2 to the 5th plus 1 divided by 2 to the 4th, and that all equals 1. Everything that was inside the brackets is equal to 1. So 3 squared is 9 times 3 plus 3 divided by 32, which is 2 to the 5th. And for the 1 over 2 to the 4th, we have to create a common denominator. That becomes 2 over 32. And when added all together, we realize that 32 divided by 32 equals 1. All those processes got us to the place where the initial value went through the entire Collatz sequence using the rules, and in the end, it equaled 1. Now, seeing it another way, if we didn't think of 3 as just 3, and it was a variable like x, 3 squared is 9 times x, 2 to the 5th is 32, plus 3 divided by 32 plus 2 divided by 32, we get an equation 9x plus 5 divided by 32 equals 1. In this case, x equals 3. This is the equation for the Collatz sequence for the positive integer 3. For the number 4, it's even. We use our first 2. 4 divided by 2 equals 2. 2 is even. The second 2, 4 divided by, in this case, 2 times 2, equals 1. 4 divided by 2 squared equals 1. Number 5, 5 is odd, so we multiply by 3. First 3, so 3 subscript 1, and then we add 1. From here on in, I'll avoid using the subscripts, because I'm sure you understand what's happening. 3 times 5 plus 1 equals 16. Within that bracket is 16. We divide that 16 by 2. It gives us 8. Within that bracket is now 8. 8 is even. 8 divided by 2 is 4. Now within that square bracket is 4. 4 is even. 4 divided by 2 equals 2. What's in that bracket now is 2. 2 is even. We divide that by 2, and we get to 1. Everything in that bracket is 1. Then we simplify, and we get the fractions that we have to work out. 15 plus 1 divided by 16 equals 1. Put it another way, we've used 1, 3. So 3 times x in this case. X would be 5. 3x plus 1 divided by 16 equals 1. In this case, x equals 5. This is the equation for the Collatz sequence for the positive integer 5. For x equals 6, we see a pattern. You can see the processes that were 3x plus 1 clearly in the brackets. We see the number of 2's that we've applied. And when we look at the result, we get 3 squared, and you'll notice there is 2 3's. So 3 squared times x. There was 6 2's used, so 2 to the 6th in the denominator. And then when we work out the fractions, it's 10 divided by 2 to the 6th. And in total, it's 3 squared times x plus 10 divided by 2 to the 6 equals 1. In general terms, it's 9x plus 10 divided by 64 equals 1. For x equals 7, we look at the same thing. The number of 3's in this case, 5. The number of 2's that we used during that sequence, 11. When we work out the fractions, we get 347 divided by the common denominator. So in this case, the equation for number 7, using the Collatz rules, is 243x plus 347 divided by 2048 equals 1. For number 8, of course, there's only 3 2's used. X divided by 8 equals 1. For number 9, we have 6 3's, 13 2's. You work out the fractions, and the equation is 729 times x plus 1631 divided by 8192 equals 1 when we substitute 9 for x. So for each positive integer, there exists a unique equation that captures the steps in each Collatz sequence. Now, those are very simple numbers, and they follow sort of a pattern up till 26, and then something very different happens. For the number 27, we end up with 111 steps before it goes 4, 2, and 1. The highest number in the sequence is 9,232. It's amazing. 41 steps are odd numbers. 70 steps are even. Knowing what we know now, the equation that defines x equals 27 is, for 41 steps, 3 raised to the 41. We used 41 3's. There's 70 even numbers, so 2 to the 70 plus a lot of fractions. And when I mean a lot of fractions, I mean a lot of fractions. When you work out the numbers, and I'm going to call that fractions f, is 1.144 and all those numbers times 10 to the 21st. It's a huge number. But those three numbers equal 1. That defines the Collatz sequence for x equals 27. One of the wonderful aspects of studying mathematics is the journey that it takes you on. It's very much like the paths that the numbers take from their initial value of x to their conclusion of 4, 2, 1. Now consider this again for x equals 9. For every even number, we divide by 2. For every odd number, it's 3x plus 1. When you see that they just continue to act upon each other sequentially, it becomes a distinct expression that takes this form: 2's, 3's, 1's, and brackets. So just multiplying by 3's, dividing by 2's, adding 1's, from the initial value of x, one after another, until the result reaches 1. And then the general equation becomes 3 to the m, where m is the number of 3's. X is the starting value. N is the number of 2's. The denominator always has 2 to the n. And then there's lots of fractions to figure out. And when we figure out the fractions with the same common denominator of 2 to the n, we get the equation that defines x. Simplified, it is 3 to the m times our initial starting value x plus f, I've used f for all the fractions, divided by the common denominator of 2 to the n equals 1 for every and any positive integer value x. When we write out all the steps as above and count the 3's and 2's, etc., f is determined by just some simple mathematics. F is 2 to the n minus 3 to the m times x for any positive integer. So all we need to do is count the number of n's, and we don't have to work through all the fractions and denominators. We can get f right away. Now, as of 2020, the Collatz conjecture has been checked by computer for all starting values up to that large number, 10 to the 70. Well, all I can tell you is by the time you're done, we far surpass that with this general equation for the Collatz. So here, then, is the fundamental equation that defines every Collatz sequence, no matter what integer x you choose from 1 to infinity. 3 to the m, the number of 3's that we've utilized throughout the sequence, times x, our starting value, plus f for all the fraction values in the numerator, all divided by 2 to the n being the number of 2's that we used during the entire sequence, and all of that equals to 1 every single time. And knowing that, we can determine what f is just from that simple equation without exception. So, every Collatz sequence beginning with a positive integer x can be written in this bracketed form, with each successive operation, whether it's 3x plus 1 or x divided by 2. The accumulated numerical and bracketed operations define the Collatz sequence uniquely and precisely until 4, 2, 1 is reached. This bracketed form of the Collatz sequence can be applied to any positive integer x from 1 to infinity. It's really beautiful when you look at it. The simplified equations that we've shown, 3 to the m being the number of 3's throughout the sequence, times x, our starting value, plus f, representing the numerator of all the fractions, divided by 2 to the n being the number of 2's we used in the sequence, for any positive integer value x. Recall that integer 27? We still get to 4 and then 2 and then 1, but for no apparent reason it climbs as high as 9,232, but no further, before descending down to 1. The sequence takes a lot of steps, 111, 41 steps in the odd numbers, 70 steps in the even. But why 9,232 and no higher? Since every positive integer from 1 to that really large number we saw has been proven to satisfy the Collatz conjecture, then every integer from this set, when multiplied by 2, results in an even number that automatically has proven path to 4, 2, and 1. Have a look. Even the highest number value that the Collatz path results in, up to this point, when it's divided by 2, in this case, 9,232 divided by 2 is 4,616. That path has already been proven to satisfy the Collatz conjecture. So as soon as we hit 9,232, we now have a determination by inspection that the very next number is already proven, hence 9,232 is proven to satisfy the Collatz conjecture. In general, having proven that any integer x subscript I will end with the path of 421, any subsequent positive integer x subscript j, always even in that case, that is twice xi will result in a proven path ending in 421, and subsequently xj satisfies the Collatz conjecture, and thus is proven by inspection. At this point, the proof is obvious, but a mathematical proof must be decisive. To that end, we are going to provide a mathematical proof by construction. Proof by construction, or proof by example, is the construction of a concrete example with a property to show that something having that property exists. Joseph Neuville, for instance, proved the existence of transcendental numbers by constructing an explicit example. So in our case, prove by construction the Collatz conjecture, that there exists a function that expresses the operations that create a Collatz path for any positive integer x that ultimately ends in values 4, 2, 1 based on these rules. For every positive integer with an initial value x, if it be an odd integer, then it is multiplied by 3 and then has 1 added to the result. If x is an even integer, then it is divided by 2. This continues until the end values of 4, 2, 1 are reached. Now, this proof is written in conversational language for everyone to enjoy, so very few symbols are included. So here's the proof, beginning with the following mathematical declarations. Z is the symbol for all integers x. It comes from the German word Zahlen. The Collatz conjecture only applies to all positive integers 1 through infinity, mathematically inclusive as defined. There are no exceptions. The 4 basic arithmetic operations in maths, addition, subtraction, multiplication, and division, for all integers are timeless, immutable, and infallible. Infinity is that which is boundless, endless. There are no exceptions for all positive integers. The mathematical equations 3x plus 1 and x divided by 2, the definition of the equal sign, the laws of exponents, and the methods to create common denominators are timeless, immutable, and infallible for all positive integers from 1 to infinity, mathematically inclusive. These and their applications completely define the mathematics involved in the Collatz conjecture for all integers. All these declarations are known, proven facts by mathematicians. To begin the proof, we revisit. We revisit x equals 6, 7, 8, and 9. And when we apply the operations of the Collatz conjecture, we find that when each operation is accounted for, the result is an equation unique to each integer x and its subsequent individual path. Here you see for x equals 6, we obtain 3 squared x plus 10 divided by 2 to the 6th equals 1. In general terms, 9x plus 10 divided by 64 equals 1. In this case, f equals 2 to the n, which is 6, minus 3 to the m, which is 2, times x. For x equals 7, we see the result, 8, 9, and 10, all resulting in an equation unique to each integer x and its subsequent individual path. And even for the seemingly most unexpected and complicated paths, the rules are the same, the brackets are the same, the 3's and the 2's are the same, numerators, common denominators. So for this larger path 27, we reach 4, 2, 1. The sequence takes way more steps, 111, 41 through odd, 70 steps through even, m equals 41, n equals 70. By some simple math, we obtain f for this specific equation that defines the path for the integer 27. For each positive integer x, we just multiply by 3's, we add 1's, divide by 2's as required one after another, until the result reaches 4, 2, 1. And then the general equation becomes 3 to the m times the starting value x, plus a lot of fractions, with a common denominator of 2 to the n equaling 1. Simplified, 3 to the m times x plus f, all divided by 2 to the n equals 1. For any starting positive integer x. See, after all the steps are completed, we simply count the 3's, count the 2's, and f is solved. Thus proven by construction, the Collatz conjecture, that there exists a distinct function for each positive integer x that expresses the mathematical operations that create a Collatz path for any positive integer x that ultimately ends in values 4, 2, 1 based on these. For every positive integer with an initial value x, if it be an odd integer, then it is multiplied by 3 and then has 1 added to it. If x is an even integer, then it is divided by 2. This continues until the end values of 4, 2, 1 are reached. Thus the proof has been satisfied, as required. Software confirmation. Using the magic of computers and some programming, the equations were verified. As mentioned earlier, according to Wikipedia, as of 2020, the Collatz conjecture had been checked by computer for all starting values up to 2 to the 68th. All integers tested eventually ended up in the repeating cycle of 4, 2, and 1. Well, I can tell you that that number has been exceeded by many, many orders of magnitude. But something occurred when we were testing the code. Here's a screen capture of the program for the relatively small numbers 145, 146, 147. We took a look at these because the program revealed some interesting observations. For 145, 146, 147, we obtain the same n values, the same m values, and thus the same f values. But they take different paths to get there. How is that possible? What was found is that there are numbers that take the same number of steps, even and odd, resulting in the same f value, and yet how they get there is always unique. Each of 145, 146, and 147 meet along a distinct path until they all arrive at the same number, 94. How they get there is unique. The two odd numbers, of course, have a different 3x plus 1 value to begin with, which takes them uniquely along to 94. 146 being even is divided by 2 immediately, but eventually ends up at 94 as well. What was found is that there are the occasional pair of numbers, and in this case 3 numbers, 3 successive numbers, that differ by only 1. They gather quickly to a common value, 94 in this case, taking the same number of steps, but with unique values in their sequence, after which the remainder of the Collatz sequence is identical. What is found is that there are 2 ways to get to a number. If you look at the odds, 31 times 3x plus 1 is 94. When you look at the even case, 146, 188 divided by 2 gets you to 94, and the rest is history. I like to use big pads of paper when I do mathematics. And out of curiosity, and to verify that although the same number of steps are taken, the resultant f value is the same for the different paths up to 94, in the cases of 145, 146, 147. I use these large pads when I explore mathematics, as I said, but for 145, I perform the Collatz steps by hand, determine the fractions, determine the common denominator, and then the total of the numerator for the steps as shown. In this case, for 145, the total is 12,032 divided by 2 to the 7th. For 146, I did the same. I performed the Collatz steps by hand, determined the fractions, determined the common denominator, and then the total of the numerator for all the steps. And I got the exact same results, 12,032 divided by 2 to the 7th. Now, there are, just to note, a few observations as to what the differences are between 145 and 146, and I do the same for 147 on the next page if you're curious. For 147, I did the exact same thing, and the result was completely the same. Different paths, of course, but 12,032 divided by 2 to the 7th. And of course, we did this repeatedly with many, many numbers with the software and determined that it confirms the general equation for each Collatz sequence for every integer, but it also highlights the uniqueness of each path. We had some fun. We put in some huge numbers, as you can see, underlined in red at the top. And in this case, we had 499 threes, odd numbers, 1,047 even numbers. And then we calculated f, which is that number that is underlined in yellow at the bottom. And of course, it all equaled 1, just for fun. Now, I would like to thank you for watching and listening. For more information, please visit our website, jamespmoore.com. And for a complete shift here, explore how applied mathematics has been used to create the next generation of renewable energy called the Stingray Wind Energy and Clean Water System. It is going to be the least expensive renewable in the market. Payback period of 20 months or less, 5 kilowatts AC or DC, and when that power is used, it can provide up to 48,000 liters of clean water per day. And it's designed to produce full power at the world's average wind speed of just 5.5 meters per second. Please check it out. Lastly, to honor Dr. Lothar Collatz, sir, all I can tell you is you created a perfect mathematical machine. Thank you so much.